Hey, thanks everybody for having me. I'm going to be talking about Java RCE via native serialization, but we're not just going to focus on that. We're going to focus on a variety of deserialization mechanisms that are in Java and ways that they can be exploited to achieve RCE. We'll ignore anything that isn't RCE because, you know, what's the point? So just a little bit of background on me. The photo is there not to terrorize your children, but just for anybody who look at the slides offline and wants to terrorize their children. I'm not actually a pen tester or any kind of security researcher. I never have been. I have no training or education or anything in the field. I'm actually a software engineer, and my real speciality is climate forecasting. My claim to fame is that I wrote the aviation meteorology system for the Southern Hemisphere. So if you fly a commercial airliner pretty much anywhere in the Southern Hemisphere and the pilot comes on and tells you what the weather's going to be when they land, I wrote the system that generates and transmits those messages, which doesn't really qualify me to be a security researcher, so sorry. Via a series of coincidences involving China and a stuffed walrus, I wound up leading Red Hat's Java security team for several years. Spent about 5 years focusing on Java security all day, every day. For the last year and a half, I've actually been an engineering manager for a software-defined networking company. Funnily enough, the two biggest open source software-defined networking packages, Open Daylight and ONOS, are written in Java. So the skills came in handy. So just an outline of what we're going to be talking about today. I won't read it out, but we're going to start with an explanation of the different deserialization mechanisms that are available in Java, dig into various exploits for each of them, and then start to dig into some more open research questions, and then kind of some analysis of things that have gone on in the last 6 months, issues that people have found. So there's multiple ways that you can serialize and deserialize. I'm just going to use the term deserialization, but I mean serializing and deserializing data in applications written in Java. One of the most common is various serializers that use XML as the data format. Unfortunately, Java has this affinity for XML, which is one of the many horrible things about it as a programming language, probably not the worst. One of the terrible things about the fact that it has such an affinity to XML is the JSRs, the specification libraries for XML parsers, mandate that they must expand general and parameter entities by default in any document that they parse unless explicitly disabled by the programmer. So basically anything that parses user-supplied content, user-supplied XML content in a Java app is vulnerable to XXE and XEE. We won't dig into that because it doesn't count as RCE, but I'll just throw that over the fence. But there are various ways that you can get RCE in the XML serialization implementations, which we'll look at. There's also what I'd call native serialization. So this is inbuilt to the programming language. It's in the JDK. You have a binary data format which is used, and you don't require any external libraries or dependencies, but there's some downsides to that which we'll explore. Then there's the newer, hipper, I don't know if there's anything new and hip in Java, but the newer, hipper ones like Dozer and Cryo and other serialization frameworks. The common thread here is kind of obvious. Don't deserialize untrusted user-supplied input. And that's a bit of a no-brainer. I think everybody knows that. But we're going to dig into some details there around, particularly around native serialization, where many people, including myself, contended that that was not the case. And this is a fantastic opportunity. If you've ever seen me speak before or something and thought I was a pompous prick, I'm going to admit that I was wrong at the end of this presentation, that I was actually wrong about where the vulnerability lies in native deserialization. But we'll start with some background on the XML deserialization libraries. There's a standard for this, a JSR for this called JAX-B, and the reference implementation and other implementations of JAX-B, as far as I'm aware, don't have any exploitable vulnerabilities. There's none that have ever been publicly reported. I've had a fairly good look and haven't found any, so we'll just park those to the side. But they're actually not that widely used. There are other libraries that are widely used in a variety of contexts. One of the most common contexts is XML REST API frameworks. Because Java's got all these building blocks, so you've got a HTTP communications library, then you've got an XML parsing library, you've got an XML serialization library on top of that. Just glue them all together with some abstract transformer bean factories, and you've got a REST API framework. So that's a common usage. And two of the XML serialization libraries that are commonly used are XMLDecoder and XStream. Now, a really important caveat here, which is going to have implications later on in the presentation. These XML serialization libraries don't rely on any interface that's implemented by classes. Java's native serialization library says that it will only serialize and deserialize a class if it implements a special marker interface called serializable. One of the both advantages and disadvantages of XML libraries is they don't care about this. They will serialize and deserialize anything you tell them to, which is one of the reasons why people use them. The first one is just a terrible design. It needs to be taken out behind the shed and put out of its misery. There is no redeeming quality of XMLDecoder. The idea is that you give it an XML document that describes a series of method calls, the result of which will reconstruct the object on the end that's deserializing it. So if you take a look at the example here, this is an XML snippet or XML document that's a XMLDecoder format serialized object. And what you tell it to do is say, I'm going to instantiate an object that's of this type, of the Groovy shell type. And then you say, so while you're instantiating that, by the way, can you please run its evaluate method with the following arguments? And it will just execute that code as part of deserializing. You can literally just embed arbitrary code in there and it will execute it as part of deserializing it. So anything that actually uses XMLDecoder to deserialize arbitrary user-supplied content is by default vulnerable to RCE. So, first demo. And these are all live demos, by the way, so they're probably going to go wrong, but we'll try. Is that text big enough, or should I make it a little bit bigger for people to see? Go a little bit bigger. Okay. So does this mic work? Good. All right. It will be better for this particular context. So if we have a look here, we have a very simple Restlet application. And I've got a README file that makes exploitation simple. We've got a vulnerable version of the Restlet jar that we're using to compile it. And just to make it simple, to use the same example as we did earlier, we've also got Groovy on the class path so that you can instantiate the Groovy shell class. That's actually just for convenience sake. You don't need that. You can use process build or anything in the JDK. So that's not a necessary condition for exploitation. That's just making it easy. So I'm happy to share all these exploits, by the way, if anybody wants them. So then we've compiled it. We just run a server application here, which is just binding a HTTP server to port 8182. That other step isn't actually necessary. So then we just get, make this one bigger too. We're going to run this curl command. And we're just making a call to this Restlet application, and we're passing in customer.rce.xml as the body of the post. And what you'll see is we pop up events. Oh, that's my tax return. You don't want to see that. It's appalling. So instead of popping calc, I like to pop events. This is a tribute to Mark Schoenfeld, the guy who taught me Java security before he sold his soul and ran away to work for Oracle. It was always, in all of his reproducers, he would always pop events. So I always try and do that. So if we take a look in customer.rce.xml, it's exactly what we saw on the slides there. It's just this XML document. It's instantiating the Groovy shell, telling it to execute events, and up it pops. And as soon as you pass it into a REST endpoint that's bound to use XMLDecoder to deserialize the content, it executes the code. Simple. Now it's going to go back to this start on me. Okay, so that's XMLDecoder. And it's just fundamentally insecure. So when I reported that the Restlet REST framework, which is a REST framework that allows you to plug in arbitrary serializers and deserializers, you can use binary deserialization, you can use XMLDecoder, you can use XStream, whatever you want. It's just a utility knife. And I explained this to them, and they responded by just removing support for XMLDecoder from the framework. That's why I say no redeeming qualities. XStream, on the other hand, does have redeeming qualities and is used all over the place. Spring OXM, Sonatype Nexus, i.e. what's used to run the canonical Maven Central repo. So you can see where this is going. Yes, Maven Central was vulnerable to unauthenticated RCE for years. Jenkins, etc., all use XStream to process unverified, unvalidated, user-supplied input in various contexts. So if there is a way that XStream can be leveraged to achieve RCE, a wide range of applications are vulnerable. Now, one of the cool things about XStream is that it does reflection-based deserialization. And this is necessary to support some of the funky features in Java like dynamic proxies. So there's a little diagram here that you probably can't see because of the res that explains what a dynamic proxy is. But basically the idea is you'll have an interface, and then normally you'd have an object that just directly implements that interface. So when the comparable interface has the compared to method in it, and whatever object implements the comparable interface has an implementation of compared to, then gets executed when you run it, right? A proxy is where you set up this kind of facade class where you say, yeah, I'm going to implement the iComparable interface, or sorry, mixing up with .NET, the comparable interface, and then whenever one of those members of that interface is called, I'm going to proxy that call to some other class. I'm going to pass that through and do something else as a result, which we'll get to in a minute. So what an attacker can do to exploit this issue in XStream is provide a serialized representation of a dynamic proxy class which implements an interface that the application might expect. Now, there's a cool trick to this, because what you've got to do is give it a serialized object that's going to ultimately execute RCE when some method is called, and you've got to force it to call that method no matter what. So what you do is you serialize a tree set, which is a sorted set. So all of the members of tree set implement the comparable interface. And when a tree set is deserialized, its members need to be sorted by executing their compared to method. So you give it a tree set with just a string element in it, just for funsies. And then the second element is a dynamic proxy, which uses this invocation handler called event handler. So the invocation handler is the piece that says, whenever I'm implementing this interface called comparable, whenever any of the methods on that is called, no matter what their method signature is, whether there's arguments, if there's arguments that just fall on the floor, I am going to do the following thing. In response to that event, I'm going to do the following thing. And in this case, it's construct a process builder object of events and start it. So as soon as the server receives this serialized XML snippet, deserializes it, it compares the comparable objects in the tree set, comparing the proxy one causes events to be executed. So, where could you exploit this? For example, Jenkins. The Jenkins XML API uses XStream to deserialize input. And one of the reasons that it does so is for this kind of support of dynamic proxies. It's useful. It's actually, you have to squint a little bit to call this a critical issue in Jenkins, because if you've got Jenkins configured in such a way that you can hit its XML API, there's a 90-something% chance that you can also just spin up a job. And if you can spin up a job in Jenkins, the job is arbitrary code. So you'd have to have very specific configuration in Jenkins where you allow people to do certain things in the XML API, but not to create jobs, which is a non-standard configuration. So the majority of deployments would not be affected, but some would. It's a legitimate config. So let's give you a live demo of that. Okay. Jenkins. Now I've cheated. I'm actually already running Jenkins locally because it takes a little bit to set up. I'm just going to verify that. Yes, I am. And if you have a look at this shell script that I've got, it's very simple. It's just going to use curl to make a post to the Jenkins endpoint, the create item endpoint. And then if you take a look at the document that it's using there, input.xml, it's very similar to what we saw earlier. Instead of having a tree set, you've got a Hudson top-level item, which is a similar item that will be sorted, and the same kind of approach applies. You run it. Well, events came up on my other screen. You're going to have to take my word for it. There it is. Yay. Events. So that's a simple explanation of how you can get a similar kind of issue in Jenkins. But there's a whole bunch of other vectors here. Anything that's taking untrusted user-supplied content and feeding it into XStream was, or potentially still is, vulnerable to this issue. Now, the way that it was fixed upstream was by introducing a whitelist and blacklist. And all of anything that was going to use this special proxy handler code, dynamic proxy converter, was blocked by default. So that's a pretty good solution in XStream. But they took a while to do it. It took them quite some time. Me and some of my colleagues at Red Hat were kind of poking them. We had to write a patch, try and get it through their CI process, and we're like, this is critical, hello. In the interim, several downstreams, such as Jenkins and also Sonatype, produced their own patches. Because Sonatype Nexus does the same thing, so there was a period of time at which Maven Central was exposing this, and so if you can get RCE on Maven Central, you can pollute any canonical jar you want and pollute any app in the Java ecosystem. It's kind of bad. Back in 2014, I wrote a blog post about this, which is still relevant. There really hasn't been much change to the state of the art since then. Okay, so that much is mostly background. It's useful information. We'll come back to it in a minute, but I just wanted to give you that background before we deep dive into native deserialization or binary deserialization. I'm calling it binary deserialization because it has a binary data format. Now, the interesting thing about this, I think fundamentally it doesn't have a terrible design. It makes a lot of sense the way that it's implemented, and it doesn't have any inherent security vulnerabilities. But the entry point for security vulnerabilities is the fact that when you implement the serializable interface, there are two optional methods for you to implement. You can just leave it and inherit the default, whatever it does, I don't know, or you can implement your own version. Read resolve comes before read object because there's some weird cases where you need to do some things at one point of the deserialization instantiation, other things afterwards. I don't kind of understand that either. But anyway, if any class that's on the Java class path implements the serializable interface and it has some code in these read objects or read object or read resolve methods that expose some kind of vulnerability, then attackers could trigger it by passing in serialized instances of those classes. So there's two conditions that have to be met here. The first is that an attacker has to be able to provide arbitrary serialized content, and the second is there has to be something vulnerable on the class path. So let's start with the first bit. How can an attacker provide arbitrary content and have it deserialized? Well, there's a range of ways in which you can. Some of these REST API frameworks like Restlet, they actually allow you to use binary serialization format as the basis for a REST API, which is kind of stupid because you've tightly coupled it to Java, but some people have done it. Other Java communication mechanisms like JMX and RMI also use it, which again is tightly coupled to Java, but those are much more widely deployed. Now, this is how I first became exposed to this whole category of vulnerability. And I'd like to call out Takeshi Terada. As far as I know, he doesn't really speak English. He's never spoken at a security conference. I can't find a picture of him anywhere. He is the most prolific Java security researcher in the world, hands down. Absolutely hands down. Go check out his research, and it's amazing. So I got an email in early 2013 to secalert@redhat.com, which was entirely in Japanese. And we had a policy. If you sent us an email that was not in English, we would not reply because 99% of the time it was spam, or we couldn't deal with that. So no. But I was looking at it, and it's all Japanese, and then there's all these Roman character things in there where it's like RCE, JBoss, serialization, code exec, and I'm like, no, you know what? It turns out at the Red Hat Brisbane office, by coincidence, we had the documentation translation team there with like 3 or 4 native Japanese speakers. So I went down to the lunchroom and was like, hey, you got some spare time? Can you translate this for me into English? And they did. And it still didn't make a lot of sense. What we had was this, what he'd proven was that the Rich Faces framework, which is an MVC framework for web applications, was using the binary serialized format to handle state synchronization. So you know how you can have like client-side state and server-side state, and you can have a serialized string to match them up? They were doing that with this binary serialization format. And that much we figured out pretty quickly. And we thought, okay, that's potentially a problem, but then he's got this magic serialized object that he's provided. He hasn't told us how he generated that serialized object, but he just said, I've got this magic serialized object and we could reproduce. If you feed that in as the view state into a Rich Faces app, you get RCE, but we couldn't figure out how. And we'll get to that in a minute as to how it actually works. So let's do a proof of concept where I'm actually going to write the vulnerable class just to demonstrate how this kind of thing would work. Okay. Okay, so here we've got this sort of sample application, and what we've got is customer.java. This is a very, very simple class, and we set up this customer. I got this out of I pulled this out of a unit test that was in Restlet, and the guy who wrote it's French, so it's Jean Dupont or something. I can't pronounce it correctly, and I just offended half the room. And so you've got this customer whose name is Jean Dupont, and then we've got a read object implementation here, right? So it implements serializable. It has a manual implementation of the read object method, and in that it sets the name field to be bad. So what we're going to demonstrate in this proof of concept is not crossing any trust boundary. It's just when you serialize an instance of this object where the name is Jean Dupont, you deserialize it, and it's Jean bad that comes out the other side. So we've got two versions of the Restlet jar that will illustrate this. So the first one is Restlet-vuln.jar. Yeah, and then oh, my bad. Okay, that should have persisted. Because I've already got another one open. No. This is what I get for doing live demos, people. Yeah, I might have to pull abort on this one, unless that's going to work. Oh, it's got me in Java C. I'm an idiot. Yeah. Yes. All right. I can compile Java. So then we're also just going to run a client. And here's what we see. When we deserialize the object out the other side, the name is Jean Bad. And I can show you the code. I'll post all this on GitHub. But the client is literally just making a call into that API. There's nothing fancy there. So this is just to demonstrate the issue. Okay. So the question then becomes, what kind of issue could actually exist in these methods that would be slightly more interesting than that and actually get you RCE? So the first example of this came in 2011. Anybody want to help me with the pronunciation of this Belgian gentleman's name? I've never had any clue what the correct pronunciation is. No? Okay. Well, Wouter it is. And he found this invocation handler in Spring AOP. Now, the really interesting thing is I talked about event handler in the context of the XStream exploits, right? Where we said the event handler, invocation handler, would allow you to specify a method, so you could process builder arbitrary code, that would be run when any method on the interface that you're acting as a proxy for is executed. You don't have to map it to the correct method. It's just any method is called, this code gets executed. But event handler does not implement the serializable interface. So it's only useful for those XML libraries. For the native deserialization library, it doesn't work because it's not serializable. But he found a similar case in Spring AOP where there was a serializable invocation handler that was exposed, and a very similar exploit could be put together. It was actually quite a bit more convoluted to set up the serialized object graph for this one. Alvaro Munoz has got a really good write-up because the original author never actually published an exploit publicly, and so Alvaro figured it out and wrote it up, and we'll see this exploit used later on in the presentation. But that was the first time I've researched this pretty extensively that such an issue was ever reported. And at the time, there was actually quite some resistance to assigning it a CVE ID. Mark Thomas, who's the security lead for Spring, security lead for the Apache Software Foundation, and the lead developer of Tomcat, and my arch nemesis, decided that this was not a vulnerability in Spring. This was a vulnerability in whatever application was deserializing arbitrary user-supplied content. But we'll get to that argument in more detail soon. So, back to Takeshi Terada and the mysterious Japanese report. What we eventually figured out after 24 hours and too much coffee and the precise dose of whiskey was that the exploit was actually exploiting a poison nullbyte flaw. So there is a class in the commons-fileupload library, which is a common library that's used to handle file uploads, oddly enough. And it has a class called disk file item, which is exactly what it sounds like. It's a representation in memory of a file on disk. So when you deserialize a disk file item, it implements a read object method, which actually recreates the file on disk. But of course, it doesn't let you specify the absolute path to that file. That would be completely insecure. A private member of the class, a private variable in the class, specifies the tempdir, but then the temp file name is generated by code at deserialization time, so the attacker can't provide it. But what we found was that the tempdir could get a poison nullbyte at the end of it, and the rest would be truncated when generating that file URL, so you could just say /path/to/shell.jsp, and then make the body of the file shell.jsp, and you could upload it to the server by having it deserialize it. So this raises a really interesting question. How can you have a poison nullbyte flaw in a Java app? And I would love to know if anybody has any theories as to how that is possible. Nope. Okay, so Java has managed memory. So it doesn't interpret a nullbyte as the end of a string. It just interprets it as like a Unicode character. But it turns out that actually the native implementation that it's ultimately calling in the JDK itself, the C code in the JDK, was vulnerable to a poison nullbyte flaw. So in newer versions of the JDK, I think it's 7.4.9 and 8 and above are all patched. But if you had a vulnerable JDK and a vulnerable commons-fileupload jar on the class path and an application that was deserializing arbitrary untrusted user input, you had complete RCE by virtue of being able to upload a shell. So that could be done, for example, using the Restlet framework or any of the other vectors that we just described. So how do you solve this kind of problem? Well, solution number one is obviously don't deserialize untrusted content, but there are all these cases where you want to do so. And then the second is, well, don't introduce flaws in read object and read resolve. And this is where I was wrong, because I really held on to this point and said, well, to date, as of 2013, we'd had 2 of these vulnerabilities, and both of them were kind of stupid issues in the code that never should have been there. So my contention was that the serialization design is actually good. We just need to eliminate all the vulnerabilities in the libraries. The third solution is to do type checking with look-ahead deserialization or not so serial. There's various frameworks for this now. The issue there is that if you try and type check something after you've deserialized it to check if it's on a whitelist, you've already deserialized it and potentially had RCE. So people have developed mechanisms where you can peek into the binary data stream, determine the actual type, determine if it's implementing a dynamic proxy or not, and then whitelist or blacklist it before you deserialize it. So the next bit of research I started doing was looking at this object mapper called Dozer. And Dozer is kind of a type mapping tool. So it's used in enterprise integration software where you'll have the X system and the Y system. And they will have different objects that represent a similar thing, and you'll want to do a mapping. So you might have one airline system that refers to seat count and another one that refers to passenger count. And when you're morphing those objects from one to the other, you want to just have an XML file that says, oh, passenger count on that system means seat count on that system, or something like that. And so then you can just dynamically transform objects from one to the other. And it's doing this using the binary deserialization mechanism. So if you can set up the right conditions, you could actually use this to exploit a similar issue. And I went down this kind of rabbit hole here because, and I sort of got lost. I was thinking, oh, I've got this great 0-day in Dozer. If only I can find a class that's serializable, because event handler is not, and then meets all of those conditions that we said earlier, that no matter what method is called on the interface that you implement, because you can't really influence that, you get your arbitrary code called. You don't have to line it up for some other condition in the code after deserialization to execute a method that happens to map to a method in an interface that you can pretend to implement with a proxy. That's too hard. But in the end, what I was looking for was another universal invocation handler vector that could be used here. And I went right back to Wooder's original exploit and said, well, you know, that could quite feasibly be used to demonstrate this issue, and in fact it did demonstrate this issue. I took Alvaro's implementation of that exploit, ported it to work with Dozer, and then in the end was able to achieve RCE. So that I will also give you a demo of. So this one I really cheat. I'll just put it all into a shell script. I'll run it and then I'll talk through everything that's being done here. Boom, okay. If you take a look, what I do is I create two classes. One that's called the Dachshund. I don't know if anybody, I have two of them. They're really long. And then, so they have a length property. And then you have a Corgi, which is kind of fat. And so it's got a, yeah. It's got a width property. And then you set up a, where's my... You set up an application that, and this is the instantiation of the object graph to exploit that Spring issue, which I'm not going to talk through. It's going to take all day long. But we set up a Dozer bean mapping, which maps and says, when you're converting a Corgi object into a Dachshund object, you take its width property and you turn it into the Dachshund's length property. We then instantiate this complex payload that pretends to be a Corgi, and then when you finally get its width in order to instantiate the long dog object, and you map it from the Corgi to the Dachshund, that chain gets called, and you pop events as a result. So yeah, this code is already on GitHub. I'll distribute links on Twitter at the end, but yeah, it'll just take too long to talk through it, but that's the issue. But anyway, there's nothing really new under the sun there. That's just saying this is another vector to utilize another known vulnerability in a serializable class, another vulnerable invocation handler. So all of the ones that we saw so far, commons-fileupload, Spring, these are pretty common libraries. 10, 20, 30% of Java apps would be using them. What if you could get a vulnerable invocation handler in the JDK itself? Then you have 100% guarantee that any application that's deserializing user-supplied content is vulnerable. So in Java 7 and 8, which are the predominant versions, there are 3 invocation handlers other than event handler. One of them is called the composite data invocation handler, which just forwards getter methods. It's completely useless. I just scrubbed it off the list immediately. The 2 other ones are potentially exploitable under certain conditions, but those conditions are so circuitous that I never bothered kind of reporting this. So here this is basically 0-day here, but it's just bad. It's terrible 0-day. So the MBeanServerinvocationHandler is a proxy to an MBean or managed bean. A managed bean is a deployed object in a Java application server container. And a lot of these Java application server containers have MBeans deployed by default that do nasty things like deploy war files, or upload files, or delete deployed payloads or so on. So step one, you have an exploitable MBean deployed, highly likely, if you're looking at like a JBoss server, WebLogic server, or something. Step two, you have to specify the correct JMX URL to get to that MBean. Now, a lot of the times, a JMX server will actually be bound to localhost loop back on port 1099, which in and of itself is a vulnerability, but it's often there, in which case you can easily construct that URL. If you don't have that, you can get to it. You can construct a URL using the Java process PID, and so you could just brute force all possible PIDs to get process IDs to get there. That's not so bad. Those conditions are annoying, but that would be a cool exploit if it worked in and of itself. The problem here is that the MBean server invocation handler does not allow you to say, okay, I'm going to create a proxy object that implements comparable, and then when compare to is called, any method on that is called, execute my code. It says when method called ABC with arguments of type X and type Y are called, then it will proxy through to that MBean with the exact same method name, the exact same method arguments. So unless you can somehow line this up that after deserialization, it's going to make a call to a method signature on some interface that also happens to map to the exact same method signature on an exploitable MBean that's deployed, so I just gave up. And then remote object invocation handler is basically the same thing. It's via RMI, but it has the exact same problem. It's actually easier to exploit, but again, you don't have that ability to say, we'll go from any arbitrary method call to code execution. So that's kind of where I stopped looking at this for a while and thought, oh, well, maybe that's as far as we get. And then a bunch of people went further with this towards the end of last year and made a lot of progress. And when you think about it, it's freaking obvious. I'm kicking myself that I didn't realize. Because all I was looking for was this, event handler is so neat. It's this one little class. All you need is to be able to serialize an event handler, and it does all the work for you. But really what you need to be able to do is serialize an object graph. So somewhere the entry point to that object graph is a serializable class. And then but that object graph can be as deep as you want. It can contain as many sub-objects as you want, as the Spring one does, until you finally get to an exit point that gets you RCE. And this is very similar to ROP chaining. It's, property-oriented programming is the term being used. And if Stefan's in the room, shout-outs to him for figuring this out in PHP deserialization before anybody did in Java. So Chris Frohoff et al. Put together this fantastic work here, which you should all take a look at AppSec Cali, where they drew this out. And they said, drawing the analogy to ROP, they said these are gadgets. These object graphs that can be exploited are property-oriented programming gadgets. So they found a really cool one in Commons Collection. Commons Collection is really common. It's used in pretty much every Java app. So this is fantastic. There is a patch that's sort of applied now, but it's not properly patched because of the Apache Software Foundation's assertion that this is actually a vulnerability in the deserializing app and yada, yada, yada. But they reported 4 different gadget chains that use Commons Collection, and they also reported 2 gadget chains that use the Groovy Shell jars. So at this point, they sort of said, drop the mic and walk off the stage and say, yeah, how many other gadget chains can you find? It's pointless at this point. The vulnerability is if you are deserializing arbitrary user-supplied content, eventually there's going to be some kind of gadget chain that's exploitable. Foxglove Security picked this up and said, yeah, so all you need is those input vectors. Here's input vectors in JBoss, WebSphere, Jenkins, WebLogic. The Jenkins ones they stole from me, bastards. And so on. The JBoss one they also stole from me and Arun. So at this point, everybody just says, that's it. If you're deserializing content in a Java app, you're done. So what do we do about it? The Frohoff et al., who put together that property-oriented programming research, put together a tool called YSOSerial, which does 2 things. It provides some tools that help you find gadget chains, but it also aggregates them into exploitable payloads. So there are, I think, 6 or 7 of those. It's on GitHub. As a defense, obviously the defense is to re-architect your app to not use this, but for brownfield deployments, so to speak, that's not really an option. So one option is look-ahead deserialization tools that allow you to do type validation before you trigger an exploitable condition. There's several of these now. There's one that I linked to earlier from Pierre Ernst at IBM, which is sort of the canonical work on it. But that was more like a tutorial page. And now Not So Serial and Serial Killer have come along and implemented frameworks that do this for you. And in particular, the Serial Killer framework can do it at runtime. You don't necessarily have to rewrite any code in your app. You just add it to the class path, add some configuration parameters, and it does it at runtime for you. Future research, well, more gadgets and more deserialization vectors. I think the holy grail here is a gadget that's entirely constrained to the JDK, because then you've got no other condition to be met. Every app, by definition, has the JDK there. So here's where I was wrong. When I was at Red Hat, Red Hat's a CNA, CVE naming authority. So I had the wonderful ability to assign my own CVEs, which I often did so to pick fights with people. And in this case, I did it to pick a fight with Mark Thomas from the Apache Software Foundation. He wouldn't assign a CVE for the disk file item issue, so I did. And he got very angry. And I wrote this official Red Hat blog post, it's still there, stating that Red Hat's official position is that the vulnerability lies both in the vulnerable class and in the deserializing app. So I retract my position. I believe that tweet sums it up. So, yeah. All right, any questions? Nope. No questions? Well, it must have been perfect then. Thank you very much.